Okay. Well, Hello?
Hello.
Yep. Okay, everyone is online today. Okay, let's see. Where is the... Anything you guys want to say? Oh, yeah, one point. I think, where is Matt, by the way? Matt is missing. Huh? Okay. Oh, hi, Christian. Yeah. So videos are good. Yeah. Okay. I was saying that I think last time, Jeremy, you and Matt, Curtis, were you there last time?
Yeah.
Yeah. Okay. So I think we got disconnected in the last 10 minutes, if you could recall.
Yeah.
Right. I think because of the last time's experience, you guys just left. But if you had kept a little more patience, we did come back online. And I took that opportunity to just finish the topic right there. So it is recorded. And if you go to the recording, you should be able to see the last 10 minutes. So I'll say that you should go and look at the recording instead of me going through again, because it took a good amount of summarizing to proceed. So let's move on, if that's okay with you guys.
Sounds good.
Okay.
Yeah, that's fine.
And I'm thinking that since this part created some concerns, what I'm going to do is I'm going to make one of the midterm exams. That sounds very unreasonable, but still I'll make one of the midterm exams fixing this. Like, remember that I said at the last moment that, oh, if you keep a next to leading order term, you will be able to get exactly the same answer, which I think you guys should see it. Otherwise, it's always a mystery there. At least I would not like it if it is just hanging. And the time is also a constraint. So what I'm going to do is I'll make a midterm exam question based on that, but it'll be very much explanatory, and I'll do some small part you will fill in here and there. So it won't be that you will be doing a lot of tough things in there. You will do a small piece, but it will involve a reading of the whole thing and getting a clear picture of that. So that's my fix to the issues that I think it all started with. I think you guys telling me that I think Christian started it up that way. You were not able to get the match it, right? So, yeah, good. So I think it was good, but probably, yeah, for you guys it might have been confusing. Okay, anything else? So I want to start a small thing. I want to do a couple of small things and then change gears and do dynamics completely, basically radiation, and that will also involve doing Lorentz transformation or special relativity in the context of electromagnetism. So let me begin by saying multipole expansion in magnetism. That's one thing that was not was done in electricity, so why not do it here also. So first of all, homework 6, which I'm thinking of making some new problems on this multipole expansion. So I might take a day or so to post it actually. So today is 12th, so 19th. So it is not yet posted, so I probably post it in a day or so. And midterm will be 1 week from there. So 2 weeks from today is the midterm. Is that too light? Is it readable?
Looks fine.
I don't have to change the pen, correct? It's an option I have. Okay, so let's quickly do electric multipole expansion, right? So electric multipole expansion. We did. So remember, the smallest entity is charge. Monopole, basically, then comes the dipole, electric dipole, and then comes the electric quadrupole, and so on. It keeps going on. We can talk about an L pole in terms of legendary and spherical harmonics, but typically we work with only dipole and quadrupole even. But here we might restrict ourselves to just dipoles. So, but it's just nice to see the whole where it fits in. So remember, so this is electric, right? So we talk about potential, scalar potential, right? In electric field case, it is a scalar potential that plays an important role, and in magnetism, it is a vector potential that plays an important role. So that will be the difference. And here it was 4 pi epsilon naught, and our superposition principle is that give any charge distribution and the electric potential is given in terms of this. And notice the charge distribution is what can be broken into. It is like a something like a Fourier transform, if you want. A Fourier transform is done in terms of modes, in terms of periodic modes. Here the modes are different. Here we talk in terms of another kind of classification, and that's in terms of poles, monopoles, dipoles, quadrupoles, and so on. And that expansion primarily starts from here. So one recognizes, one realizes that this, what we call the Green's function, or the electric potential due to the point charge, due to unit point charge, if you want, has the following expansion. So think of expanding it at r prime equals 0. I think we had this discussion last semester, or how do you see this as a Taylor expansion. But nevertheless, this is equal to minus r prime dotted with the gradient of 1 over r. Remember, what is gradient of 1 over r? This is the potential of a point charge. That will be the electric field due to a point charge, except for 4 pi's and 1 over epsilon naught floating around. This is just the electric field dotted with r prime, where r prime is the source function. Right? So 1 over r, and then you expand this out, and the next term is plus 1 by 2, and this time you have 2 of them. This is r prime dotted with, sorry, 1 by 2, I didn't mean r. 1 by 2, r prime times gradient, and again an r prime times gradient. Remember Taylor expansion, right? Squared quantity. This is the x, this is the squared quantity, all acting on 1 over r. Differentiate between the r primes and r's, the gradient is acting on r's, right? Not r prime, and so on. So, and you can keep doing this exactly. This is pretty much the Taylor expansion around this r of this left-hand side. If I were to substitute this in there, I won't go through the details here. This is just a summary, and it turns out that this is 1 over 4 pi epsilon naught. The first expression, notice, is r, right? There is no r prime dependence, so it can come out of the integral. Oh, I can remove my mask today because there's no. Okay. So 1 over 4 pi epsilon naught, 1 over r, that comes out of the integral, and what is remaining is E cube R prime times rho of R prime. And what is this equal to? You recognize immediately that, oh, that's the charge, right? That's the total charge of the distribution. So we started with the distributed charge, and this is the total charge, and that's a monopole, right? That's a definition of the monopole. And the next term would be, so this is now I will take this outside the integral. So that's minus of, and why is that a minus? Oh, yeah, that is a minus. Yeah, that's minus 1 over 4 pi epsilon naught. That's gradient of 1 over r. Keep it outside as it is, and dot it with explicitly writing this r prime times rho. Is that visible? Oh, I slightly went off. And you can keep going. I won't, I think in the last semester we went one more term. This is a monopole that's defined as the dipole. So this integral is defined as a monopole, which is straightforward, right? Integral of the charge density is charge, total charge, straightforward. That's your monopole. And whatever is in the second integral, this is the, notice the first moment of the charge density. It is something like center of mass. Here it will be center of charge if you want. And that's defined as the dipole. Right? And we said P, I suppose, or D. I think P probably. That's your P. And next one, similarly, will be having the quadrupole in it. And let me not do that at this point, but again, we did it last time, right? So this is 1 over 4 pi epsilon naught Q over R minus, but I can actually do this R hat over R square, right? That brings in a negative sign, so that's a plus 1 over 4 pi epsilon naught, and R dotted with P over R cube. First, you get an R square, but there's an R hat there. If I write it as R, that's R dot with P, and so on. You can keep doing this, but my point was to recognize this pattern in here, and Q is E cube R prime, oops, R is to 0 rho of R prime, and P, the magnetic moment, is the first moment. So this is vector R prime. And quadrupole moment has, in very simple terms, 2 of them, but since there are 2 of them, it can be symmetrized in many ways. So the quadrupole has a slightly different form in which it can be written, but it is pretty much, in simple terms, it has 2 position vectors. It's a second moment of the charge density. Okay, so this is what we did in electric case. So now we want to do a similar construction for a magnetic case. So let's see, magnetic. Move this camera. So magnetic multipole expansion. So here we begin with the vector potential. So this is A R equal to U naught over 4 pi times Q prime, then J prime divided by R minus R prime. Right, that's your magnetic vector potential, and of course, once we have the vector potential, magnetic field is given in terms of del cross. And since we have very similar expression there, one is very tempted, or it is very natural if you want to say that, okay, why not again expand the 1 over R minus R prime and collect the terms, and if we can put this all together, we should get a multipole expansion for the magnetic case also, except the feature that this is all vectors there, right? There it was scalar, now these are vectors, so they will combine in different forms, but nevertheless we should be able to see it, and we should be also see that remember the monopole case there was a total charge, and here the magnetic monopole case, that will be the total number of north poles available if you want, which is 0, we know, right? There is no isolated north pole, so always it comes for the south pole, so the charge is always 0. So the first term should go to 0, and the second term should come out to be the magnetic magnetic dipole. So let's see how this goes about. Right. First, let me recall what your magnetic moment is, right? So magnetic moment is, how do you define that? We use this in our homework, and I introduced this before, but let me put this in the context we need. We will need a particular form of this magnetic dipole moment. So M would be equal to charge. If it is a single point charge, then we say the charge divided by the mass of the charge, and since if it is moving, then it has some, so this is Q over 2M times, if it is moving, it also has some angular momentum, R cross momentum, right? So it is angular momentum, L. So that's a simple, if you are a discrete quantity, it is just a magnetic moment of a charge, single charge, is just the ratio of Q over M times the angular momentum. And we did this, we used this to calculate the magnetic moment of a simple loop if it was rotating. But it is nice to see this in slightly different form. This is this could be confusing, right? This is M is the mass, that's your magnetic moment. But this is, let me not change that. Keep this in mind that this is M, it's not the magnitude of M there. Okay. But if I were to extend this, it has the simple feature that, remember, L is R cross MV, where M is the mass now. M and M cancels out, and I can see that this can be written as R crossed with Q times V. And the moment you see Q times V, you think of current, right? That's a current for a point charge. Right? Q multiplied with V gives the idea of a current. And then if you want to think of it as density, then it's immediate. You immediately lift this to charge density, and this becomes a current density. And you say that if there was a charge distribution, your generalization to this is not equal. So this is a generalized definition if you want, or maybe I should not even, right? That's a magnetic moment of a distributed charge or charge density would be equal to an integral of R. So that's your R prime, let's say, crossed with the current density. So that's QV gets upgraded to current density, and R is exactly the same, and that's your magnetic moment. So we want to keep this because that's what we want to identify, right? Inside inside this expression, when we are going to see the construction, we should look for this. That's our magnetic. In general, for an arbitrary distribution, that's our magnetic moment. Okay, so that's one thing. And also recall, so a bit of summary here. Also recall that we are doing magnetostatics. Magnetostatics. Move the camera. So magnetostatics had this assumption that the divergence of the current density in general is equal to generally equal to the rate of change of charge, right? This is the flux equation. That's d rho over dt is equal to 0. That's a conservation of charge principle. But if you're in statics, this is equal to 0. You assume that there is no change in the charge density. So in magnetostatics, we also have the divergence of J is equal to 0. So these are the ingredients we're going to use to recognize a nice multipole expansion for the magnetic case. Okay, so any questions at this stage? This is all summary for now. So now let me get into the actual multipole expansion. So A is equal to mu naught over 4 pi t cube prime, and again this is just rewriting prime over r minus r prime. Just put it up again. We again have the same thing that we did earlier. This is equal to. Notice that we did this last semester, but it is good to observe, right? This is, I mean, I wrote this expression as a series. It's good to notice that this is simply r prime dotted with the gradient exponential of this. Think of this as a series, right, acting on 1 over r. So this whole operator sits on the exponential, and that's that. That's just a recognition, but if you don't like that, if that is too abstract, just take this as a Taylor expansion, and it is equal to 1 over r minus r hat or r prime dotted, or the directional derivative with respect to r prime, right? That's what it is. 1 over r, and that's our first term. If you were to expand an exponential, remember exponential of minus x is 1 minus x plus 1 by 2 x squared, and so on. This will be negative. That's the first term in the expansion, and we will stick to just the first term. We won't go beyond that. Okay. Next term will be the quarter pole. Right. And let me write this as plus. So that's good. So I put this back in here, right? Exactly what we did in the scalar case. Place that inside that expression and try to interpret the two terms. It's mu naught over 4 pi, and this is d cube r. 1 over r comes out of the integral, so that's 1 over r. What remaining is the integral over current density. Right? Earlier we had an integral over charge density, and now we have an integral over the current density. Let me write the second term also before I come here. Notice that this whole thing comes out, right? This is a R dependent quantity, 1 over R, and the gradient acting on that. That's all a R dependent quantity. It doesn't have to sit inside the integral, so it can come out. So it's minus of mu naught over 4 pi, and this is a dot product, so I can change the order of that. I write it outside gradient 1 over R dotted with R prime. Now notice, be careful here. Oh, am I within the? Yes, I am. I have a lot of space there. And that is a J. Be careful in interpreting this. Notice this is a dyadic, right? Inside the integral, there is no dot product, there is no cross product. The first vector is dotted with something outside the integral. So left hand side quantity part of the dyadic is dotted with the gradient of 1 over R, and the right hand side is the free vector, which gives you the vector feature as a whole. Okay. So that's what it is, and we will come back, and there are higher terms, right? But we won't address that here. Right? Our goal is to show that this is actually a monopole, and that's a dipole, right? And remember, dipole, the way I introduced it, there was a cross product of R cross R and J. So that R and J does show up there, but it is not a cross product. This is not at all a cross product. So we have to process this and show that actually this is a cross product. Okay, but before that, we know that magnetic monopole is 0. So apparently, this should be 0, right? Maybe. Right? Is this 0? Right? We don't know. Right? That's not very obvious that that's equal to 0. So let's see. Let's define this, or let's not even define, let's just try to evaluate this, right? So let's take a digression right here and try to show that this probably is 0. So for that purpose, that's what I try to introduce. Remember our divergence of the current density is equal to 0, right? So one would think, oh, is this related to this somehow? Yes, it is related to that somehow, but it's not immediate, right? Even if you were to take an integral or use a divergence theorem, you don't get that. If I were to integrate that, I only get the flux of the current density equal to 0. I don't get the fact that as a vector integrated over all space, that's equal to 0. Of course, J are it's a current loop, but one might wonder that does that all happen? It is because these are all loops of current. There is no source of J anywhere. That is why it is happening. But let's check this out. Is there a more explicit way of doing this? So how you go about that is how you want to show this. So you have this divergence of J. If that is the case, I can always multiply by a vector, right? So if something is 0, if I multiply that with the vector, that's also equal to 0, right? If something is already 0, if I multiply quantity to it, that's perfectly okay. So that's okay. That means if it is 0 at every point in space, if I integrate that, that's also equal to 0. So this is also equal to 0. Q R, and let me write this as like I can write the R on the other side also. So it's J times the vector R is equal to 0. that's perfectly okay. If that is the case, but we want J, right? So you immediately think that, oh, okay, maybe we can take the integration by parts, and that's exactly what we will do. Let's integrate by parts. Then there are two terms in there, right? So first is, I can hit the gradient on both. That's a boundary term. Remember, integration by parts, one of them gets integrated and you get a quantity only on the boundary, right? So this is the one on the boundary. So that's, but it's still dotted, right? It acts on both, but it's still having a dot with the first quantity. Now we see the dyadic quantity. This has this feature of the dipole feature in there, but let's not go digressed. We are interested in the monopole part. And we should integrate by parts. This leads to EQR. And the second piece is when you hit the gradient on the other vector, right? But still dotted with J. So notice vector calculus piece in here, like we've done this kind of stuff before. The gradient moves, acts on the other vector, but still it is dotted with the earlier J, right? So it is in a sense now a directional derivative with respect to J. That's what it is. So that's also equal to 0. Okay. And this should give you some idea of how this is going to work out, or how we are going to show that the integral of J is 0. First, we say that this is acting only on the boundary, right? This is, if we were to integrate over the whole universe, we say that at the surface of the universe, there is no current. So our system is confined in a lab space, which is probably few meters or something. And if you're observing very far, so it doesn't go, all the energy dies off very quickly for closed systems. And in that case, this is equal to 0. Right? If so this is equal to 0, if J is equal to 0 on boundary. And this is crucial, notice all these assumptions, because we are saying that this is an arbitrary configuration we are talking about. We are not taking a specific example and doing it. So it's important to realize that what are the assumptions we're making. We're saying that J always has to go to 0 as we go to the surface of our universe. And that should bring us back to our, I think this was a discussion that came up. If you have a line charge or line charge density, right? A current loop that goes all the way along the z-axis, starts from -infinity and goes all the way to +infinity. That's really not completely physical or not consistent with our assumptions here. But then we try to make it length L and try to do some justifications of that. So with that, now if this is 0, but still we don't have this J, right? But now it is kind of clear. What is this quantity? If I were to put a parenthesis there, and what is that equal to? We have used that a lot this during this semester and last semester. You recognize that? You guys are muted probably. You guys don't realize if you're saying something. How much is that equal to? No? No one wants to say? What is this equal to? As a dyadic?
Is it just the unit dyadic?
Yes, that's the unit dyadic, right? So this will be just the unit dyadic, right? Always we have been instead of always going at each step and calculating it. In the beginning, we said that if we recognize this, we don't need too many derivations. So this is also the completeness statement if you want. So that's your unit dyadic, but that's one, and that immediately gives you, oh, this is that means this is 0 minus d cubed r, and j dotted with 1 is just j itself, the current density itself, and that's equal to 0. And that tells us that the monopole, like this was the total, if you want, this represents the total north pole, right? Total charge. Like when we say total charge, we mean the total positive charge. If it comes up negative, then it is having a negative charge there. So similarly, if this is 0, that means the north poles and south poles all balance out all around. But and that's the statement that magnetic monopole doesn't exist. So that's good. So the first term is 0. So we are left out with the second term, and we want to recognize the second term as the magnetic moment again. And let's go back and look at this equation. So what we have here is, if I were to go back up, so I've shown that this is equal to actually 0. So this is a statement that no magnetic monopole. But that's okay, because if I were to say that is QM, so I'm actually saying that this is there is a magnetic, that could have been a magnetic monopole, but it is 0. And now we are to similarly say there is a magnetic moment, right? M is equal to 1 by 2 cross product there. So this is R prime crossed with J. But where is it? It is not very obvious that this is actually equal to that. So, so let's write this as, erase this. So my goal is here that A of R potential is equal to mu naught over 4 pi times let's say this is J, how do you call it? Yeah, capital J, let's say. So it's capital J. Like it does not depend on any position. This is R dependent, so that's your R, so that's your monopole. So this is equal to 0. That's equal to 0. Plus, and now we would like to see if this is possible, mu naught over 4 pi. And we know that if there was a magnetic moment, we know what its vector potential is. So we would like to see this as R crossed with M. No, so this is M crossed with R. So this is order dependent now. This is M crossed with position R over R cubed. And there will be quadruple terms. And our M is this, but it is not at all clear how you can recognize these two. Yeah, we do see the R over R cube showing up there. But how is this a cross product at all? So that's the challenge. For that, we again go back to our what's the divergence of J being equal to 0. And let's try to quickly see this. So what we did earlier was we started with J is equal to 0. Right? So that was our first thing that we did. But then we said, okay, if that's true, then this multiplied by a vector is also equal to 0. Okay. And we could show that integral of j is 0. But now we will do something more. I will actually multiply one more vector to it, but not as a cross or dot. This will be as a direct. And since now this is already getting too many vectors here, let me go to index notation. So I'm going to use, this is m times jm. That means this is dotted, right? Whenever the indices repeat, that means it is dotted. And these two are free, so I keep that as, let's say, A and B, right? Since there is a J, I don't want to use that. Let me use this as K, maybe. Let's say this is K, and let's say this is M and N. No, or M or N is equal to 0. That's that's always true. If this is 0, then you can multiply it with a 0 again. Right? Integrate this over all space, and then integrate by parts. The same trick that we did earlier, a few steps back. So integrate by parts as a boundary term, which goes to 0. That's K. K. And there is a boundary term, J of K, R of M, R of N. But that is 0 because J goes to 0 at the boundary. This survives only on the boundary. And next is EQR. Differentiate by parts. So it's J of K times divergence, this time acting on Rm. N. Very similar to what happened earlier. This gave you a 1 there, a unit dyadic, but this time there are 2 of them. That's the only difference. This is again 0 because it's on the boundary. And what we have here is that, let me expand this. So I have 2 of them. So there's a negative sign, I don't have to care about that. So that's d cubed r. When k and m act on that, that's a unit dyadic. That gives me k gets replaced with m. So what I get here is a j of m times r of n. And when it hits on the second piece, that's again a unit dyadic, but this time the different index comes in. So it is just, if I were to replace the index, I'm good. So this is j of n, which is best written by moving j on the other side, right? So this is m times jn. M jn. If I were to write this as a vector quantity instead of indices, still after all the process, we have actually only 2 vectors. At this point, it is possible to do this as vectors. So this is j and r, because notice the indices are placed correctly, plus r times j is equal to 0. There is some information about the first moment of current. Like remember, whenever we multiply a distribution with a vector position and integrate it, that's called the first moment. That's like center of mass, if you want. Center of mass is the first moment of mass, if you want. So the first moment of current density is 0 in the symmetric sense. It is not that it is completely equal to 0, but if you take the right combination, then it is equal to 0. If that is the case, then we go back and remember that we got the dipole moment to have a, so if I were to move this just this side, So this expression here, this has R prime and a J. Right? This is an R prime and a J, but in a different form. So it seems like maybe we can do something here. So let me do the following. So E cube R prime times R prime times J. Let me forget the primes here. Let's keep it here. R primes and J. That's what it is equal to. But I want to use this results that we just now have. So let's done the following way. I first of all add and I make two pieces of this. So this is R prime J, and I keep one more R prime J. I can always do that. I keep it at a distance because I'm going to do adding and subtracting. So there are two of them now, but I divided it by 2. It's just a trick. Now, in the next piece, I want to get the other term in here. So I'm going to add a J times R prime. So this is the reversed quantity. And if I add that, I will subtract that. It's minus J times R prime.
Could you move the camera over a little bit?
Oh. I moved it this side, but then I forgot it. Yeah. So what I did was that I first put two pieces in there and then divided it by 2, and then I subtracted 2 quantities. So it's just a trick. I'm playing algebraic trick there, but that is so that I can use this result. So this is equal to 0. So I get an antisymmetric combination of R and J, and that will give us the cross product. Right? Antisymmetry cross product is antisymmetric, and that will help us get that. So that's this quantity. So my expression in there. So this is equal to, if you want, right? I'm going to how about this? So I'll do gradient of 1 over R. Am I within the boot space? Yes. And let me also, yeah, so dotted with d cube R prime J. This was what our expression was to begin with on the left hand side. And that leads to, I'll take this inside for a moment and bring it out again. So this is d cube R prime. This is jotted, so think of this as a vector, dotted with R prime, and then there is a free vector J. Think of your back cab, right? So there's a, and minus of, now I flip the dot product, so this is 1 over R, dotted with J, and there is a free vector R prime. If you think of your back cab, double cross product, this is nothing but 1 by 2 e cube R prime 1 over R crossed with R prime crossed with J. Seems like a big expression, but notice recognize the magnetic moment inside of that. This is 1 over R piece. This can come out. So that's what I'm going to do now. So this can come out. And what I have is that the vector potential A is equal to, that was minus mu naught over 4 pi. And there is gradient of 1 over R that can come out, and we have crossed with 1/2 integral d cubed r prime r crossed j. Oh, it was, sorry, I think I meant to say it the other way. I think back cat, right? Sorry. So when you do the back cat, this is j crossed with r, like j is the first vector, right? So it is j crossed with r, so there's a minus sign in front. There's a minus sign in the front because j is the first vector, so it should be j crossed with r hat. But then you can use the cross product property to flip that with the minus sign. And if you use that, come back and put that in here. So there's a negative sign in there, and there is that makes this a positive sign. And that's r prime crossed with j. You recognize the magnetic moment there. And if you were to use the explicit gradient here, so this is mu naught over 4 pi times minus of r hat over r square crossed with m. But that's okay, because cross product, again, I will flip it and to get the sign fixed. So it's mu naught over 4 pi, that's m crossed with vector r over r cubed, which is exactly what we proposed. So we now get the feature that, oh, there is this multipole expansion in that. We'll now do some simple exercises, like we want to, this is abstract, very general. What if you have some current loops? How do you actually get the total magnetic moment? It's basically adding vectors to it. And we'll do that as examples next time and go from there. Thank you. Yeah, let me stop.
Okay, I did make those corrections that you suggested earlier, so I'm gonna run through my